In this example, we are going to be talking about how to do a derivative with something that's a little bit tricky. It's an exponential because you have a variable in your exponent, but then the base is an exponent as well. Normally, that's not the case, right? Normally, we have something more like this, where we have some value that is raised to a power, but we know what the base is. It's just some value. And when we do our derivative, it's going to be itself times the natural log of the base times the derivative of the exponent. So we need to rewrite this. We need to manipulate it. So it's called a tower function. And here's what we can do. So I'll show you how we can kind of manipulate something to a power, right? We're going to take this idea that somehow this actually can be rewritten like this. So let me show you how that works. So if I just set this equal to 0, just so I can kind of have an equation out of it. And I'll show you how this will manipulate to this, right? So if I have an exponential, anytime I want to bring an exponent off of an exponential, I can log it. I'm going to natural log it, right? If I rewrite that, I have the natural log of y equaling x times the natural log of b, right? And so another property I have is that if I want to get rid of logs, I can exponentiate it. So to exponentiate it, I'm going to make both of these values exponents and have the same base on them. Okay, so they're still equal to each other. What this does is it re-cleans this up into just a y, and then now all of a sudden you have this, right? So that's how that becomes. So what we're going to do is the x is the b, and the sine x is the x. So we're going to rewrite this as e. Right? So our exponent is sine x. So sine x. So sine x times the natural log of our base. So times the natural log of our base. All right, so it doesn't seem like it's any easier, but it allows us to do our derivative a little bit nicer. So let's do our derivative. So derivative of an exponential is itself times the natural log, and then times the derivative of the exponent. So the exponent is a product rule. So the derivative of the first, derivative of sine is cosine x. And remember that the derivative of a trig is also a chain rule. So the derivative of sine is cosine times x times the derivative of x, which is 1, and then times the second times the natural log of x plus the first times the derivative of the second. So the derivative of the natural log is 1 over x, and then technically times the derivative of x, which is just a 1. All right, so there is our first part of this. We'll do some cleanup. So that's legitimately our derivative. We just now need to clean it back up. And then there's one last little thing that we're going to pull back. So we're going to talk about that in a second. So our derivative is e to the sine x times the natural log of x times, really not much we can do with this, cosine x natural log of x plus, if I clump this together, let's just make it into one fraction, sine x over x. So almost done. It's kind of, we did originally have this look to it, and this is actually equivalent to this, and I still have that piece. So I'm going to go back and sub this back in. Since these two are equal to each other, I can rewrite this exponential back into its original terms. So our slope equation looks like this. Cosine x, natural log of x plus sine of x over x. All right. So that's your slope equation. And here they want you to evaluate this. So that's just us plugging in some values. So let's do the slope. So I can make this fit. Squeeze it down here. The slope at pi over 12 is going to be us doing pi over 12 raised to the sine pi over, it's not 12, it's 2, That's much nicer. Pi over 2. I was kind of a little concerned about my 12s. That wasn't going to be working out very good. So pi over 2. So there's pi over 2, and then times cosine of pi over 2 times the natural log of pi over 2 plus sine of pi over 2 divided by pi over 2. All right, so sine of pi over 2, cosine of pi over 2, all those are pretty reasonable values. So if I think of sine, as this. This is our pi over 2 value. And if I think of cosine looks like that. That's our pi. Oops, sorry. That's our pi over 2. That's pi. Well, there we go. So pi over 2, sine of pi over 2 is going to be 1. Cosine of pi over 2 is going to be 0. Let's finish plugging all these values in. So we have pi over 2. Sine of pi over 2 is 1, so raised to the first power, times cosine of pi over 2 is 0. So 0 times the natural log of doesn't matter, plus sine of pi over 2 is back to 1. So 1 over pi over 2. All right, so let's keep going. So this is just a pi over 2 times 0. That's going to go away. And then this, instead of dividing by pi over 2, I'm going to multiply by its reciprocal, 2 over pi. And that is going to, you're multiplying legitimately by its reciprocals, everything's going to cancel, and you're left with the 1. So that represents the slope of this equation at that value. And that's our final answer.